dear students. Today in this session, let us see more problems on type 1, type 2, type 3, type 4, that is analytic function, complex variables, finding the derivatives and finding the harmonic conjugates and many more. So take a first example. Given that f of z is equal to x cube into 1 plus I, x cube into 1 plus I minus y cube into 1 minus I divided by x square plus y square if z is not equal to 0, and the same f of z is 0 if z is equal to 0. So what we need to do is show that f of z satisfies CR equations at the origin. So this is what is the question. So we have to evaluate f of z and we have to show it as analytic at it satisfies the CR equations at the point 0, 0. That is what we mean. So solution here is given f of z is 0. So consider f of z is 0. It means that u and v are also 0 because f of z is u plus iv. Since f of z is 0, u is 0 and v is 0. So obviously our x and y also will be zeros and zeros. So now once u is 0, v is 0, ux, vx, uy and vy. All the partial derivatives of u and v with respect to x and y also leads to 0. So when we look at these derivatives, f of z is 0 when z is 0 is analytic at the origin as they satisfy CR equation. Ux is equal to vy and vx is equal to minus uy. So since CR equations are satisfied, we can say f of z is analytic at the origin. Now consider the other part of the problem. The other part of the problem is f of z is equal to x cube plus 1 plus I. This is the given problem, x cube plus 1 plus I, and z is not equal to 0. So let us take this as f of z now. So when we take this at the origin, f of z is indeterminate because when you substitute x is 0 and y is 0 and evaluate your f of z, it gives here 0 by 0 form. And 0 by 0 is an indeterminate form. There is no particular value assigned for it. So now once f of z is indeterminate form, ux, vx, uy, vy are also indeterminate. So now consider your f of z and segregate that the real and imaginary part from that. So once we do that, x cube minus y cube by x square plus y square plus take I common and write out the remaining terms are the coefficients of I here. So it gives the imaginary part for me. That imaginary part is x cube plus y cube by x square plus y square. So u is equal to x cube minus y cube by x square plus y square and v is equal to x cube plus y cube by x square plus y square. So now let us find out the derivatives of u with respect to x and y and v with respect to x and y. And let us also evaluate the same at the origin, that is 0, 0. So consider your u and differentiate partially with respect to x. So once we do that, by the definition of the differentiability, ux means limit as delta x tends to 0, u of x plus delta x comma y minus u of x comma y by delta x. That is by the definition of differentiability, u with respect to x. So evaluate this ux at the origin, that is at 0, 0. X is 0, y is 0. That is what the meaning. Substituted in the above equation, so we get this. And on substituting the limits and on simplifying, we get delta x by delta x whole cube by delta x square whole thing divided by delta x. So ux leads to the value 1. On simplifying, we get ux is equal to 1. So similarly, find here u with respect to y. So when we do that, by the definition of differentiability, uy is this, and uy at 0, 0 and substituting we get this, and on simplifying we get uy is equal to minus 1. So now consider here v and differentiate v partially with respect to x and y. So for that you can also use the basic definition of differentiability. So what is vx is? Limit as delta x tends to 0, v of x plus delta x comma y minus v of x comma y by delta x. Similarly, substitute x is 0 and y is 0. So on substituting in the above expression, we get this, and simplifying further, we get vx is equal to 1. We get vx is equal to 1, and find vy, that is partial differentiation of v with respect to y. So by the definition, we have this, and at 0 comma 0, we get this expression, and on simplifying, we get this, and vy is equal to 1. So you can observe, now you have found ux, uy, vx and vy. Compare the values. So when we compare, we get that ux is equal to vx and vx is equal to minus uy. If they are the CR equations, it means that the f of z at z is not equal to 0 satisfies the CR equation, and therefore we can say it is an analytic function. So that is what was the first problem. So now let us see another example. Another example with this problem too. The statement of the problem is determine the analytic function whose real part is y plus e to the power of x into cos phi. So given u is equal to y plus e to the power of x cos phi. Why we have taken it as u? Because it is specified the real part. Therefore we take it as u. So once we take u is equal to this, find the derivative of u with respect to x and y. So on differentiating with respect to x, y should be treated as constant, and keeping all these things in the mind, when we differentiate, we get e to the power of x into cos y is as it is, and differentiation of y becomes 0 because differentiation what we are performing is with respect to x. Therefore ux results in e to the power of x into cos y. Similarly, differentiate u partially with respect to y. So when we do the differentiation with respect to y, the x term should be kept constant. So e to the power of x acts as a constant here. Differentiation of y with respect to y is 1, e power x is a constant, and differentiation of cos y is sine minus sine y. So we had got that. And now consider here f dash of z, which we know that as ux plus ibx. And we also know by CR equation that Vx is equal to minus Uy. So using that in this expression, we get f dash of z is equal to Ux minus I into Uy. Substitute for Ux and Uy, which we have already the data, which we have found in the excuse me, which we have found, and we get this expression. And now since f dash of z is there, the next step is going to be substitute x is equal to z and y is equal to 0. So on substituting that, we get f dash of z is equal to e to the power of z minus I, and we need f of z. So we are going to eliminate the differentiation from here. So we have to perform the integration with respect to z. So when we do the integration with respect to z, we get f of z is equal to integral of e to the power of z minus I into dz plus c. So now f of z is equal to e to the power of z minus I into z plus c. This is what is our f of z. So now let us take another example. So example number 3. So if f of z is equal to u of r comma theta plus I into b of r comma theta is analytic, and given that u plus v is equal to 1 by r square cos theta minus I sin 2 theta, and r is equal to r is not equal to 0. What is need to be found? Determine the analytic function f of z. So the question is very clear. Given as u plus v, it is a type 4 problem which we have discussed, and so it has been asked us to find the analytic function f of z. So now given u plus v is equal to 1 by r square into cos 2 theta minus sin 2 theta, determine or differentiate this with respect to r partially, because polar form must be given. You have to differentiate once with respect to r and the other time with respect to theta. So ur plus vr is equal to differentiation of 1 by r is minus 2 by r cube, and cos 2 theta minus sin 2 theta is constant because differentiation is with respect to r here. And now differentiate with respect to theta partially. So when we do the differentiation with respect to theta partially, u theta plus v theta is equal to 1 by r square. This acts as a constant, keep it as it is. And this term in the previous expression is to be differentiated. On differentiating, we get this. Now use the CR equations in polar form, which are given by ur is equal to 1 by r into v theta, and vr is equal to 1 by r minus 1 by r into u theta. So on using them, in equation 2, we get equation 2 becomes u theta will be equal to, so u theta is minus r into vr, and v theta would be r into ur. On the other side, from here you can take out 2 as a common term, and we are writing it here. It is sine 2 theta plus cos 2 theta. Minus also has been taken it outside. So now u r minus vr. Take out r as a common term, and you can transfer towards the other side. U r minus vr is equal to minus 2 by r cube sine 2 theta plus cos 2 theta. So call this as equation 3. And now you can solve our equation 1, which is in the previous slide, and equation 3. So when we can solve these equations simultaneously, we get 2ur is equal to minus 4 by r cube into cos 2 theta. So which implies that ur is equal to minus 2 by r cube into cos 2 theta. So we have found u now. So now we have to find v. So from equation 1, you can find out the expression for VR. So we know the expression for UR, use that in equation 1. So VR will be equal to minus 2 by r cube cos theta plus 2 by r cube sin 2 theta minus UR. That is our equation 1. So substitute for UR in the next step. And this term, it is a positive term, and here it is a negative term, so they get cancelled. So this term and this term gets cancelled. We have only 2 by r cube into sin 2 theta. So now substitute for ur and vr in f dash of z expression in polar form. F dash of z is given by e to the power of I theta ur plus ivr. So e to the power of minus I theta is, keep it as it is, substitute for ur and substitute for vr. So when we do that, we get an expression for f dash of z. So once we get f dash of z, the next step would be substitute for r is equal to 0 and theta is equal, r is equal to z and theta is equal to 0. So once we do that, f dash of z is equal to, this is what the expression we get, and f dash of z will be minus 2 by r cube. But our aim is to get f of z. So integrate this expression. So we get integrate with respect to z. So we get f of z is equal to 2 times of integral 1 by r cube dz plus c. So integration of 1 by r cube is this, and f of z is equal to 1 by z square plus c. So this is how we'll be working out more problems, and this whatever the session we have discussed now was a tutorial session. So in tutorial session we have solved more number of problems. So thank you.